Okay, today we're going to give a brief introduction to the Intel x86 architecture. So we're going to talk about the instruction set. The Intel x86 processor is a dominant processor for laptops, desktop, and the server market. Okay, we're seeing more and more ARM-based processor for this market. For example, we have Apple M1, which is based on the ARM. It's super fast, right? So the ARM or MIPS or RISC-V, these are based on the philosophy of a RISC computer, reduced instruction set computer. Intel has a complete different design. It's called a complex instruction set computer. So the instruction set of Intel processor are very complex. It can do multiple things which can be done by several instructions over the RISC computer. Of course, in today's architecture design of Intel processors, a single Intel instruction will be decoded into a microcode. First, the microcode is somewhat similar to an instruction in our RISC computer. Okay. So here is the evolution of the Intel processor. The first one is the 8086. So then we have a 286. Then we have a 8386. Okay. So those are the number of transistors. If you look at the number of transistors, it started with 29,000 transistors. Now we have billions of transistors in a single processor. So the architecture of and the design of the Intel CPU is becoming more and more complex, right? The Intel has this concept called backward compatibility. It means that the today's processor, like Core i7, can still run software written for the 8086. Okay, so in the beginning of the computing, when vendor release a new machine, they will have a new architecture. This will break the backward compatibility. It means that the software written for the old computer will not be usable to by the newer computer. So Intel introduced the concept of backward compatibility and win the market. Okay, here is a diagram of the Intel processor. So this is a quad-core CPU. CPU. We have 4 CPU cores. Okay, those are 4 CPU cores. They have shared level 3 cache. In the CPU, you probably already know there are a lot of caches. So we have a L1 cache, L2 cache, and L3 cache. Normally, L1 and L2 are dedicated to a CPU core, and L3 is shared. Okay. So over the years, Intel has added a lot of additional features like multimedia support, like a lot of security. So Intel has added a lot of technologies like SGX, like MPX, like MPK, like VT. VT is for virtualization. SGX to run a piece of software securely in an isolated environment. Those are for the security features. And so Intel added a lot of features to their processor. Their processor become more and more complex. So in security, we know complexity leads to vulnerability. So this is why in recent years we have saw a lot of hardware-based vulnerability for Intel's processor. Okay, So it also transition from the 32-bit to 64-bit architecture. So we know 8086 is a 16-bit architecture, right? Then 386 is the 32-bit architecture. Then they introduced the 64-bit architecture. So I was at Intel when they transitioned to the 64-bit architecture. Okay, those are the recent generations. So normally, Intel processor will have a project name like Kobe Lake, right? KB Lake, like Haswell. So those are the processor names. In the this is the state of art in the 2018. So we have how many CPU cores? Here we have 6 CPU cores, right? Six cores. So they have distributed level 3 cache. Okay, so there is a interconnection between those CPU cores. So if you think about this, when you schedule a process on one CPU core, right? If you need to migrate it to another CPU core, you need for those two CPUs to exchange status, like the cache data, right? So the cache needs to be, for a process needs to be migrated to another another CPU core. So there are a lot of data exchange between those CPU cores. This is why it's important to have a very fast interconnect between CPU cores. So there is also GPU in the CPU. This is called the iGPU, integrated GPU. Okay, so when we talk about the x86, we have to talk about the AMD. The AMD licensed the CPU architecture from Intel, right? So they can produce a separate designed Intel processor or x86 processor. Okay, so AMD used to have a lot of trouble, and they lag behind the Intel. Now they actually lead or ahead of the Intel for a bigger margin, right? So they have their CEO, very famous Lisa Su, is a CPU architecture scientist. She has led the AMD to surpass the Intel in case of the CPU performance, and also they are gaining a lot of market share. So today's x86, the 64-bit x86 architecture was actually designed by by AMD, right? At that time, Intel tried to, when they designed the 64-bit architecture, they actually work with HP, try to propose a new architecture. It's called Itanium, or they call it IA64, so which is not backward compatible with their older CPUs. So AMD says, "Oh, okay, no, we are going to develop a 64-bit architecture, which is backward compatible with the older x86 processors." So eventually, AMD wins the race. So now, if you look at the kernel source code, okay, so the 64-bit x86 architecture is called AMD 64, right? So because it was designed by AMD. We have talked about this. So the Intel tried to attempt a radical shift from IA32 to IA64. It's called Itanium. It was actually co-developed with HP or HP Enterprise. So it tried to execute the i32 code as a legacy code, but the performance is very disappointing because the Itanium have a different architecture, right? So they need to try to interpret or emulate the IA32 instructions, which usually it's very slow. So AMD proposed this 64-bit architecture, right? So then the Intel followed the AMD to develop the IA32. Okay, so now all the CPUs, x86 CPUs, it support a 64-bit architecture. So today, since all the CPUs they support x86 architecture, this slide will focus on the 64-bit architecture. So the most concepts are the same and also are applicable to a 32-bit architecture. Okay. So when we talk about the like CPU architectures, so here let's first talk about the level of abstraction in the uh, in the today's computing system, right? So we have a source code, which is usually high-level source code, like C or Rust or Go. This high-level programming language, it will be processed by the compiler to produce the binary, right? So the binary or executable can be run on the computer hardware, right? So normally, if you only work at the high level, you only need to know the source code, the high level programming language, right? So and how to compile it. If you are security research, you need to know at least at this level, okay? So the security research needs to know at least the binary level and the executable level, but also you should know something about the hardware architecture. So those are very important concepts for the security researcher. So when we talk about this computer system, there is a program visible state. Like here we have something like a program counter or the instruction pointer. So the instruction pointer, it points to the next instruction to be executed, right? It's called IIP in the x86 64-bit architecture. It's called IP or the instruction pointer in the 32-bit architecture. So interestingly, for the 64-bit architecture, so there is a register called IIP. You can actually access that. Okay, but for the 32-bit architecture, you cannot directly access IP. So we have memory. So the memory is just a byte addressable array from the point of view of your processor. So it's just number of bytes. Okay, each are individually addressable. You can send an address to the memory bus, then access the content in this byte. You can also access the data in like 4 bytes or 8 bytes, right? So the code and the data are actually stored all in the memory. So this is um, together. This is the von Neumann architecture, right? So you store the code and the user data in the same memory. So it's not the Harvard architecture. To the registers, we have a lot of general, we have a limited number of general purpose registers. For the x86 32-bit, we have 8 general purpose registers. For the 64-bit, we have 16 general purpose registers. So there is also a condition code. Condition code can store the status information about the most recently executed instruction. It's used for conditional branching. So Intel architecture is interesting, right? So you execute an instruction. Then it will write the condition code into a register called eFlags. The eFlags register contains a lot of conditional code. So every instruction, almost every instruction executed will have a side effect to update the eFlags register. Okay. Now, if you need to do the conditional code, conditional branching, you can test those eFlags. So here is the data type we used in the assembly code. You can access the data in 1 byte, 2 bytes, 4 bytes, or 8 bytes. So the floating point are 4 bytes, 8 bytes, or 10 bytes. Right? There is also a single instruction multiple data vector data type of 8, 16, 32, and 64 bytes. Okay. So the code are actually sequence of the byte encoding the instructions. So x86 has something called a variable length instruction set. So it means that the length of individual instruction in the x86 architecture, they are different. So from a single byte to 15 bytes. So the shortest instruction in the x86 architecture is 1 byte. The longest is 15 bytes. So a single instruction is 15 bytes. So in the memory, you have those stream of bytes which encoding the instruction. Right? Some instruction are single byte. Some instruction could be 2 bytes. Some instruction could be 3 bytes. Right? But an interesting question is, so because the x86 architecture has variable length instructions, so you don't know where is the start of each instruction. So what if, right? Instead of the real instruction boundary, what if you hijack the control flow into the middle of an instruction? So the CPU will actually start executing at this location, and it will try to interpret this byte sequence as valid instructions. So now you are creating instructions not exist in the original program, right? For the original program, the first instruction starts here, second starts here, the third starts here, okay? But when you try to jump into the middle of an instruction, you now your instruction starts here. It could be, say, 2 bytes. Now your next instruction starts here. Now suddenly you have a very different sequence of instructions than the original program. Okay. So from the point of view of assembly code, there is no data type such as arrays or structures to then It's all bytes of data in the memory. So here is the uh, uh, x86 general purpose registers. So these registers can actually be accessed in like 64 bits or 32 bits. Okay, so this is actually a single register. So if you say RAX, you access this whole register. If you reference it with EAX, you access the NOAA 32 bits over the RAX register. Okay, so this is similar for other registers. If you look at this side, this side actually the same as the 32-bit architecture. Of course, for 32-bit architecture, you only have EAX, EDX, ECX, right? You don't have those part of the register. The 32-bit architecture contains those 8 registers. So when they extended the architecture to a 64 bits, the first they extended the register to a 64 bits, right? But they also add additional 8 registers. And for 64-bit architecture, you have 16 registers. When we compare this to RISC computers, it's still a small number, right? So for the RISC computers, you often have 32 registers or even more, okay? So here is a list of the 32-bit registers. So we have EAX, ECX, EDX, EBX, ESI, EDI, ESP, and EBP. So those 2 registers are special registers. It's called a stack pointer and the base pointer. So we're going to talk about those a lot when we talk about the buffer overflows. So the stack pointer, so we all know the stack, right? So in the x86, this is the high memory. This is the lower memory address. So the stack goes down. So the stack pointer points to the top of the stack, okay, where the data is being added or where data is being pushed or popped. Then we have the base pointer. Base pointer points to the frame of a function. We're going to talk about this later, right? So the originally, those registers, they have a specific usage. Like EAX is something called an accumulator. So the ECX is the counter. So now those are mostly obsolete. So you don't have to remember this. It's just a general purpose register. You can use those as general purpose registers, right, for any purpose. But some instructions, they're actually hard coded which register to be used, right? So, but you don't need to know too much about that because the compiler will take care of it. So for the Intel instructions, it can we have all those different kind of operations. You can transfer data between memory and the registers. For the RISC computer, right? So this is the same. You can load the data into registers. Then you can perform the arithmetic function on registers, right? On 2 registers. But the Intel being the complex instruction set, it can actually perform computation not between registers, but also between register and the memory, and also between the register and a constant. Okay, so this is different, right? So for RISC computer, all the operations are between register and register. But for Intel architecture, you can actually perform the operation between register and the memory. So because you need to reference memory in the Intel instruction set, this is why we have a variableness instruction set, right? If you think about it, to encode the memory access, you need to have more bits, but you don't want every instruction to be very long, right? That's a waste of CPU, waste of memory space. So this is why Intel proposed this variableness instruction set. So their idea is that for instruction used very frequently, you are going to have a shorter encoding, shorter instruction length. For the complex instruction, you can have a longer encoding or longer instructions. Okay. Then we also have branch instructions. We have unconditional branch and the conditional branch, and also indirect branches. So here is an example to move the data between the source and the destination. Okay. So there is a very important thing to remember. The Intel document use this special kind of use this kind of encoding. So it's the destination first, then the source code, then the source next. But for GCC or GNU assembly or GAS or LLVM is another compiler. They all use this format. So you have the source first, then destination operand next. Right? This is different from the Intel document. When you read the Intel document, you need to keep this in mind. Okay. So the operand can be immediate, like this number. It can be used as the source. But it can also be registers. So it can be one of the 16 registers, like RAX, like R13. But ISP, again, ISP is for the stack pointer. It can also be memory. Like for example, normally when you see this parentheses around a register, it means that the address is contained in this register, and you are trying to access the memory points to by this address. Okay, so this is how they express, say, access the memory. So here we have some simple examples. You can do immediate and registers and the memory. For example, this was set at IX to 4, right? So here, this is another example. You can move this number to the memory points to by the RAX register. Assume that the RAX is points to the variable P, then this will be equivalent to this C code. So you basically put this number to the address points to by IX. You can also move the between registers or move between from register to the memory. You can also move from memory to the register. So those are the different combination for the move instruction. So you cannot do the memory to memory move, okay? But in some case, you can actually do the memory to memory operation. There is something called a string instruction. But we don't need to get into those details. Here is a different method to or different encoding to address the memory, right? So we have in the previously we gave example of say this simple example, right? So you put a parenthesis around a register. So you basically so this register contains the address, and we're accessing the memory point to by this register. Then you can add a displacement. A displacement is a constant with register. Now, what we are accessing is the memory to the address equals to IX or the R register plus D, right? So here we have example. So the address is RBP plus 8. Then we're going to access this memory. So we are basically loading from this address into the RDX register. So here we have a simple example. So this is actually a swap function. So if we look at this, right? So the RDI is actually so when we call a function in the x86 architecture, right? So the first parameter is in the RDI instruction, RDI register. The second parameter is in the RSI register. So we first load the memory points to by RDI, the first parameter, to IAX, right? Then we load the second memory content to the RDX. Then we save the RDX into RDI. Then we save the IAX to RSI. So this is basically a swap function. It's going to swap the content of two memory locations. So here we show this example. Right, we have those two long parameters. So again, this is in the RDI register. This is in the RSI register. So we first move the XP to a temporary. So this will be this instruction. This will be this instruction. Then this will be this instruction. This will be this instruction. Then the return from this function. Okay. So to understand the swap, so the RDI points to the memory. So this will be the variable xp. This is the variable yp. Okay, so the RDI points to variable xp. This points to yp, right? So then we load this memory into a IAX. So the IX is T0. So the IDX is T1. Then so we load this memory to assume the address is 120. So we first load uh, the memory address of 120, the content of this location into the IX register, right? So now we copy the memory content into the IX register. Then the next instruction, we copy the memory content in the RSI into IDX register. Then we're going to write the IDX into the first memory address. Then we are writing the IX into the second memory address. Okay, so now we swapped the memory content of those two addresses. So here is the complete memory addressing mode. So it's actually very complex, right? So we can have a displacement. There is a base register. Then there is an index register. Then there is a scale. So why do they need this kind of numbers, right? Think about the case to address an array. Say you have an array B, then we have say an index. Okay, if we try to convert this into assembly, we have the address of B, which is in the base register. Okay, so we loaded the address B into our base register. Then we can have the index, the I, put it into our index register, right? Then we can add a scale. So when we need to find the memory address of this element, so we basically do the B, the address of B plus I plus multiply by a scale. So the scale is the element size, right? For array, right, it can be say 8 bytes. Our element can be 8 bytes. Then the scale will be 8. Okay, so Intel, had this complex memory address format to support this kind of user case to index into our array. Here we have an example of this computation. So for example, this one, so the address will be IDX. So here, this will be RDX plus 8. Here will be RDX plus RCX. This will be RDX plus RCX multiplied by 4. Here will be RCX multiplied by 2 plus 0x80. Okay, so this is the addressing mode to how to compute the address for this addressing mode. This is basically to put in this data. Next, let's talk about this typical instructions. So when we talk about the security, you need to understand this LEA instruction. This is very important. It's somewhat confusing. LEA is something called a load effective address. So it's basically computed address. Right? If you look at the previous example here, right? For example, if we have a move instruction, right? They move the IDX, RCX to RAX. So we basically computed the address. So this will be so the CPU will compute the address IDX plus RCX, then access the memory and put the content into the RAX register. But if we have an LEA instruction with the same encoding of the addressing mode, so what this instruction do is just calculate the memory address. It will not access the memory. So this is basically what it does is calculate the RDX plus RCX, the address of the memory, and save this into the RAX register without accessing the memory. Okay, so the load effective instruction just calculate the address. Okay. So that it's used to compute the address without memory reference, right? So this is can be used to translate this kind of instructions, like you get the address of an array of element. Right? We have mentioned this before, right? So the X will be put into our base register. So the I will become our index. Then, because it's an array, we need to have a scale. Now, if we would do the get this address using LEA, it will just calculate this address and assign it to a variable. So this is different from P equal to xi. In this case, we are actually accessing the memory, right? So the here we have a get address sign. So if you are confused about those two, you need to refresh your knowledge of C pointers. Okay. But this, if you look at this, right, so you can also use this LEA instruction to do simple calculation. Okay, you can compute arithmetic expressions of this form, right? So the Intel included this addressing mode intended to compute the address without a memory reference, but the compiler often can use this kind of instruction for different purposes. So here it's actually used to compute the arithmetic operation expressions. Okay. So here we have an example, right? We calculate the x multiplied by 12 if you look at this, we have a RDI. So the X is in the RDI. As we have mentioned, the first parameter is loaded in the RDI register. So if we have this, right, we have a RDI plus RDI multiplied by 2. So now we have a RDI multiplied by 3. Then we do our right shift by 2. So this will equal to RDI multiplied by 12. So the compiler try to generate this kind of instruction because the LEA instruction is much faster than multiplication instruction. Okay, so the compiler will try to, use whatever instruction they can to improve the performance. But another example, right? So we have some need to say set a register to 0, but in this case, the compiler often use the XOR instruction to XOR itself, right? So if we have this instruction, it will actually calculate the EAX XOR EAX and save this to a EAX register. Now any number XOR itself will be 0. So this will basically set the EAX register to 0. Okay, so here we have some common arithmetic operations. We have addition, subtraction, multiplication. This is a shift right, shift left, shift right. Another shift right. It's but it's different kind of shift. We have XOR and instruction or all instruction. Okay. Again, the entire document uses opcode, destination operand, and the source operand. This is different from what GCC use. Okay, so there is also an increment, decrement, negative and not instruction. The increment add a number by 1, decrement number by 1. Then we have negative and a not 2. Okay, so the difference between those is here. We have a negative. If we have 5, if we do the negative, we get a negative 5. But for the not, so we converted this 5 into its binary format and invoke each bit. Okay, so you get a different number. So here we have some examples here. So let's just look at the first several instructions here. So again, when we call a function, the first parameter is in RDI, the second is in RSI register, right? Then, if you look at this, x plus y, so we first do the LEQ, RDI, and RSI, then put this into RAX. Okay, so when we do this, right, so the LEQ instruction will just do RDI plus RSI and save this to RAX. So we don't need to use the add instruction. We can use the LEQ instruction. It will be faster than the add instruction, but it also serves the purpose. Okay, so the RAX now contains x plus y, right? Then we can add IDX to IAX. So the IDX is Z. Z is in the IDX. So now IAX contains here, it's T2, right? Equal to Z plus X plus Y. Then we do this one, ISI plus ISI multiplied 2 in the IDX. Okay, now IDX is actually 3 multiplied by Y. Okay, then we do our right shift by 4. Now right shift by 4. So this will be 48 by multiplied by Y. Right? When you shift by 4, you multiply by 2 to the power of 4, that will be 16. So now IDX will be 48Y. Okay. So now we can do, when we do this one, so the RCX will equal to 4 IDI will be, IDI is the X plus IDX. IDX will be 48 multiplied by Y, then plus 4, right? So we have this displacement here. So the RCX will be X plus 48Y plus 4. If you look at this T5 here, T5 is T3. T3 is X plus 4. T4 is 48Y. So RCX now contains T5, right? Then we do the multiply of RCX. Again, RCX is T5. IX is T2. Now the register contains the IAX, and the RCX contains the T2 multiplied by T5. Okay, now we return. So the EAX will be returned. Okay, so if you look at this side, right? So we have a lot of add instructions, multiplication instructions. But if we look at this side, we use LEA instruction for a lot of that purpose, because LEA instruction is faster than most of those instructions. Okay, we have covered this. So here is steps to turn C into the object code. You have the C program, then you do the compiler. Okay, you compile it with say with GCC, then you will assemble it. So, but when you do that, you pass -s to the compiler, it will produce assembly code. But normally we just do the -o and give it an executable name, right? Then p1.c, it will generate a binary. Okay, so you don't need to invoke the assembly separately. You just invoke use a single instruction. Then the assembly will call the linker. So because for almost all the C program, it will be linked into at least the libc. library, right? So libc is a shared library. Okay, so it contains a lot of functions such as printf. So if you write a program, say call printf, it will be linked into libc. When you execute the your generated binary, it will call the printf in the libc function, libc library. Okay, so here is some more examples. We can take a look at the generated code. Okay, so um, we have covered most of this, but let's do a quick demo. Do a quick demo, okay? So we have a simple program here. So this is a very simple program. We have a number, then we do a number of conditional branches, right? For each conditional branch, we're going to call a printf function. We can gcc -o -g -o. So the -g is enable debugging. So it will contain debugging information. The -o says, okay, generate the program and put it in to this binary. Then we'll give you the source code. Okay, right? Now you can see we have a binary here. It's just generated. Okay, we can execute this binary. Okay, so the value is 1. If you look at the original program, right, the number is 1. Now we test the number is 1. So it says the value is 1. So we are taking this, and this branches, right? And so to disassemble this program, right, you can use obj dump dash. Let's put a magic parameter. It's called dash s, the capital S. Then condition, say condition.asm obj dump obj dump. Let's say here we have the additional the assembly code. If you look at this, there are a lot of things we didn't put here. So those are the directives to support the program, right? So we need to find the main function. Let's just do a quick search. Okay, so this is the main function here. If you look at this program now, there is a main function. Okay, so we saw a lot of conditional code here. So if you look at this carefully, we have the original C program interleveled with disassembler code. So this will help you understand how compiler generated the code or convert your high-level program into those assemblers, right? So the way to do this is two steps. The first, when you compile the program, you add the -g. This will contain all the debugging information. Then when you disassemble the program, you use this /S. It will do the mixed disassembly. So basically, it will disassemble your program interleveled with the source code. Okay. So here, for example, for this one, we have a local variable assigned to be 1. So if you look at this, right, so then we know if we look at this mixed assembly, we know this local variable is allocated on the stack. It's on the RBP -4. So we're going to talk about the stack layout. So this is actually very important. So you can understand the layout of the stack. To understand like a simple exploit like a buffer overflows, you need to understand the stack layout, right? How the different local variables are placed on the stack. Then you can decide how to overwrite those variables with the buffer overflow vulnerability, right? If you have this kind of mixed disassembly, you can tell, say, this local variable number is at this location, right? Okay, so this will be very useful to help you understand the disassembly of the uh, Intel architecture, okay, or any architecture, right? So try to compile some simple programs and do the disassembly and say if if you can understand those instructions. Okay, let's stop here for this part.